Recently, we've been building confidence intervals for population means. And in building those intervals, we have made one simplifying assumption. We have pretended as though we know the population standard deviation, sigma x. Well, in the case of our penny population in class, we really did know that population standard deviation. So we were able to use it when we were building our confidence intervals. In most practical settings, though, you don't know that. So in its place, when you build a confidence interval, you replace the population standard deviation with the sample standard deviation. Of course, now in building that confidence interval, there are two values that come from our sample, both the sample mean and the sample standard deviation. So there is additional variability within this confidence interval because now there are two unknowns. Understand then, we need wider confidence intervals to capture the same level of confidence. And to build that wider confidence interval, instead of using z-scores, we use t-scores. T-scores are based on, instead of the normal distribution, well, they're still based on the normal distribution, but it's a t-distribution. And when you look at that t-distribution, it simply has more area in the tails. And that allows for the additional variability for which we would like to account. Let me see if I can show you that, or at least demonstrate that on my calculator. So what I've done here is the standard normal density function. That's the one that you have been used to working with. So here is a t-distribution. So notice right now the calculator is graphing it. Notice out here over to the left, the tail, there is more probability out here in the tail on the left, and then just like the standard normal distribution, it's symmetric, so there's more area in the tail on the right, and less of that area then is captured in the middle. It is still a probability density function. The area under this t-distribution is still 1. It's just that there is more area out in the tails than there is in the center of the distribution, and this is what allows us to account for this additional variability. Now, something to think about though, as your sample size rises, let me go in here to my y equals menu, as the sample size rises, so I don't expect you to enter these things into the y equals menu, I just wanted to show a graph of it. So here again is the standard normal density function. So here is what the t distribution would look like, and you can just barely see it graphing. You can see a little bit plotting right here and here. We'll see it plotting up here just ever so slightly. It varies ever so slightly from the standard normal distribution, and this is because our sample size is 30. So once you have a sample size of 30 or more, the t distribution and the standard normal distribution, they look virtually the same. So you'll see very, very small differences in between them. So the bottom line is the bigger the sample size, the more and more normal this distribution will look. So the t distribution is based on that normal distribution. So we still talk about using normal methods within this context. So let's take a look then at the example from our last class. So what we did, this is one period's worth of data. I'd like to build a 70% confidence interval. And for this period, the sample mean was 1992.97, and the sample standard deviation was 9.4. This was all based on a sample size of 30. So that sample size of 30 we will still use within this expression here for the standard error of the statistic. We'll take the square root of 30 in the denominator. Now notice up here, instead of using the population standard deviation, and in our penny population that was 11.9 years, we're going to replace it with the sample standard deviation. So our sample mean goes in exactly the same place. It will go right here. So what's different though is instead of using the inverse norm command to find our critical value, we are going to use the inverse t command, or you may be using a program on your calculator in order to find this value. So let's go back and look at, for 70% confidence, how would we be finding this value if we were using the inverse norm command? Just to review. So review, if I draw my standard normal distribution here, for a 70% confidence interval, I would like to capture the middle 70% of the distribution. And that means essentially I'm cutting out the upper and lower 15% of the distribution. So I need to find these cutoffs right here. These are the cutoffs that I'd like to find. Those are my two z-scores. So when we did this before, you could use inverse norm 0.15. Remember, the inverse norm command accepts a percentile. So if you wanted to find this lower cutoff, you could put in the percentage of the area at or below that cutoff. That would be 0.15. If you wanted to find the upper cutoff, you'd have to put in 70 plus 15% or 85%. That would be 0.15. Either way, you're finding the lower or the upper cutoff. So let's just review how to do that here on the graphing calculator. I'll go to second variables, inverse norm. So again, I could put in my area. I'll put it in as 0.85. I'll find my upper boundary. There you go. If you had put in 0.15, you would have gotten negative 1.036. So now understand, here is that 1.036. The only reason I wanted to calculate it now is because I want to compare it to the t-score we are going to use. Again, in this situation, we're not going to use this z-score here. We're going to end up finding a t-score, and that t-score is going to be just a little bit bigger than the z-score, and that will make an interval that's just a little bit wider, and that helps us account for this additional variability due to the fact that we're using the sample standard deviation, not the actual population standard deviation. So a couple of ways to do this then. If you have a newer calculator, so I will use my calculator emulator to demonstrate this, you're going to want to follow the instructions on this first paragraph. If you have an older calculator like the one I use in class, you're going to want to follow the instructions here similar to the second paragraph. So let me go through the first paragraph. Back to my calculator emulator. So to get this t-score, again, you want to press second and variables, and then the inv-t command is the one you want to use. If on your calculator you don't see this command, don't despair. That means you need to skip to the second paragraph, and in class I should have put a program on your calculator that will help you do the same thing, so just hang on for a second. If you don't have the inverse t command, it's fine. So notice for the area of the inverse t command, you can enter exactly what we did with the inverse norm command. You can enter the 0.15 or the 0.85, either way. I'll put in the 0.85. So the only thing that's different is this df. df here stands for degrees of freedom. And this is something that we've used before since we are using the sample standard deviation. To calculate that sample standard deviation, remember we divide by 1 less than the sample size. In this case, 1 less and then 30 would be 29. So we have 29 degrees of freedom, and the t distribution will look different depending on how many degrees of freedom you have. So it's important that we enter that degrees of freedom. And now we can go back to the home screen and execute the command. So our t-score 1.055, if you had entered the negative 0.1, rather if you had entered 0.15 here, you would have gotten the negative boundary, the negative 1.055. Either way is perfectly fine. So guys, if you don't have the inverse t command on your calculator, you'll have to use a program that I put on your calculator. That's what this second paragraph describes. You need to use the inv-t program. Let me show you how to do that. So I've put it on my old calculator. Oh, it's running right now, forgive me. Let's clear it, and I'll show you how to get to it. So you have to press the program button, PRGM button. So you want to select the program titled INVT, press enter. Then you have to press enter again to execute this program. The first thing it will ask you is for DOF, that stands for degrees of freedom. So just like before, we will enter the 29. And then alpha. In this case, alpha is the amount of the distribution that we are cutting off, either above or below that critical value. So notice from my picture here above, I know we're not calculating a z-score right now, but it's the same idea. We're cutting off the upper and lower 15% in order to get 70% confidence. So what you want to enter is the 0.15. And you'll have to let the calculator chug along for a second. That's what this represents right here. It's thinking, and there's the 1.055 again. So either way, you're going to get that same critical value, whether you use the program or you use the inverse t command on your calculator. So on the back side then of this handout, you can see how this confidence interval is actually built. And notice, compare, we're using the 1.055. That is slightly bigger than the 1.036 that you would get using the inverse norm command. There's the difference. This interval is going to be ever so slightly wider, and again, that's accounting for the additional variability because I'm using a sample value here, the sample standard deviation of 9.4 rather than the population standard deviation, which in most situations we don't know. So this is built just like before. Here is our sample mean. Here is our critical value, the 1.055. It's just now a t-score. Here is the sample standard deviation. We still use the square root of the full sample size, the square root of 30. So here is our confidence interval. And again, guys, it interprets exactly the same way. You should include three things when you write about a confidence interval. We can be 70% confident, so you always describe your level of confidence, that the population mean date in the class penny population, so in context, it's important that you write about what population mean you are trying to capture. We can be 70% confident that the population mean date in the class penny population is between these two boundaries. You should always state your boundaries, 1991.16 and 1994.78. So those are the three things important to include when you write about a confidence interval. Notice, just to remember what the confidence level means, this interval, we do know from the penny population that the actual true mean of the population is 1989.3 years. So let's review then what 70% confidence means. Again, if we repeated this procedure many, many times, say 100 times with exactly the same sample size of 30, around 70 of the 100 or 70% of the intervals would capture the true population mean. Of course, that means that around 30 intervals won't contain or capture this truth, and it just so happens that the interval that has been constructed up here happens to be one of those intervals that didn't capture the truth. Of course, the only reason that we were able to identify that is because we know everything that there is to know about the population in our class penny population. In most situations, you don't know all of that information. If you did, you wouldn't be bothering to build a confidence interval in the first place. So this level of confidence, remember then, describes the procedure used to build the interval. It's important you know the difference between how to interpret the confidence interval versus how to interpret the confidence level. So in terms of the conditions necessary to construct an interval for, and look at this, there's an important typo here on this handout. The conditions necessary to construct an interval for not a sample mean, this should be for a population mean. We use the sample mean in order to construct the interval, but the interval is trying to capture the population mean. So those conditions are, just like before, randomness. The sample must be a simple random sample, or an SRS. We have an independence condition, so the population must be at least 10 times the sample size, so this is the condition that we have been using to check that all along. And then we also have a normality condition, so remember a couple of things. If the population distribution is known to be normal, then this condition is satisfied, no problem. So if we don't know that, then a sample size that is 30 or more, that will also be sufficient. But something to recognize, even if you don't have a sample size of 30, these procedures using the t critical values can still be used under some additional checks that you want to look for. So for a small sample, a sample size of less than 15, if you don't know anything about the distribution of the population, you're going to have to look at the distribution of the sample. So if the sample data appear symmetric and don't have any outliers, so if they appear close to normal, then you can go ahead and use these same procedures. Of course, you need to graph the data to verify this. I would graph the data as a histogram to verify some idea of its symmetry. You could use a box and whisker plot to determine if there are outliers or not, but I would definitely use a histogram to get an idea of the shape. For a sample size of at least 15, so between 15 and 30, as long as there are no outliers and there isn't any strong skewness, again, it would be okay to use these procedures using t critical values. I would offer there can be a little skewness. You just don't want to see a lot of skewness. Once again, you want to graph your data in order to verify this. These are the tProcedures. Hope this has been helpful.